In section 4.3, we're going to look at how understanding operations with fractions will help us multiply and divide rational expressions. So oftentimes students either shy away from fractions or struggle with them, and so we're going to work with those skills and hopefully build them, but now use them in our rational expressions. They do give us some steps here on example 1 on how to solve or reduce rational expressions. They say to first factor the numerator and the denominator. We've been factoring forever and it's not going to go away. Find the domain. Remember, those are all the real numbers except for the ones that make the denominator equal 0. We never want to divide by 0. And in our inverse operations, we can't take a number times 0 and make a constant. So we'll be watching for those places in the denominator where the x value would make it go to 0. And then finally, remember that a ratio of common factors equals 1. That'd be something like 5 over 5. We have something in the numerator and the denominator. They both have that factor. It would reduce down to 1. Remember also, a rational expression is something like this. Okay, that's a quotient or a division of two polynomials. So I'm going to take that same polynomial, and I mentioned factoring is not going away. So my first step was to factor. You'll notice in this video, I do a lot of the factoring for you. It's already there, so you may want to look in your packet ahead of time and try to factor those if you are looking for that full credit. But if we factor, we took out an x, and then we factored this trinomial into two binomials. And we can look right from here. We want to stop when we first get it factored before we reduce it. We want to look at what values would make the denominator 0. So for the domain, we would say it's all real numbers except x equals 0, x equals -9, and x equals 8. If I put those values into each of those factors in the denominator, we would have a number divided by 0. So we want to do the domain second. Remember, the first step is to factor. The second step is to name your domain. And then we want to reduce. That means I will take factors that they have in common in the numerator and the denominator. Something divided by itself would make 1. Same thing with these x's. So my final answer for this first example would be x plus 3 over x plus 9. Sometimes students will look at this last value or parts of the factors and think they can reduce here, but that is not the case. We can never reduce fractions if they're connected by a plus or minus sign. And so we only reduce when they're being multiplied. Notice how the operation in between each of these terms would be multiplying because we factored them. That's why we can cross them out and we cannot reduce or cross cancel here. Now, some of these examples and tryouts are going to go quite quickly because I've already factored them for you. But on this try it, notice how the x minus 7s will cancel. The 3 and the 2, you always want to check the coefficients, but they don't reduce at all. But here I have x times x times x, and here I have it 4, if you will, x's. So 3 of them will go away, just leaving 1. So my final answer would be 3 times x plus 1 over 2x times x plus 7. Now, we do want to remember about the domain. So when it says give the domain for your expression, I kind of violated my first rule. I've told you to factor first and then give that domain. We want to use the original one here. So we would say it's all real numbers except 0. 7 would go here. 0 times 2 would make 0. 7 right there would be a problem, and -7 right there would be a problem. So with this question 1, it says, why does the simplified expression have the same domain as the original? Because here we still have 0 and -7 as numbers that would make our denominator 0, but we need to include the original one. So it's just a simplified form of it. Also, it asks, how does the denominator only affect the domain but not the numerator? You can take nothing, no apples, and divide it among 4 people. But if you had 4 apples, you can't divide them absolutely nowhere and put them 0. So this is our problem, dividing by 0. For example 2, one edit in the packet here, you'll notice this throughout some of the videos. We want you to change this top of example 2 to x squared minus 4. Here you'll see me factor it, and this time I'll say and practice what I told you to. The domain would be all except x equals 2 and -5, and that comes from here and here. Now if I reduce these, the x minus 2's cancel, and all we're left with is x plus 2 over x plus 5. To make sure you've simplified a rational expression, just be sure that the numerator and the denominator do not have a common factor left. I'm going to highlight this again because it will happen to some of us. It is not legal to cancel out these x's. Why? Because they are connected to their numbers by a plus sign. So do not try to cancel those out. Our final answer is x plus 2 over x plus 5. For the triads, same thing. Make sure they're factored. You'll find the final factored versions on each of these. We would know that 0 would be a problem here, 3 would be a problem here, and -1 would work there. So these are your domain restrictors. Here we'd have -4 and +1. And if I cross these out, we'd have x plus 1's cancel, and we would be left with x minus 1 over x times x minus 3. And you don't need to multiply that back together. We actually prefer it simplified so we know you reduced it all the way. Here you reduce the x minus 1's and the x plus 4, and that's just left with x plus 1. So the first two examples are all about just reducing rational polynomials. When we move into example 3, we're going to be looking at multiplying rational polynomials. Now you'll actually notice we're going to start with the triads on example 3. They're a little bit easier to work with, but let's talk about multiplying fractions before we start multiplying rational polynomial fractions. If you were to multiply 2/3 times 1/6, you would be able to just simply multiply the numerators, 2 times 1, and then multiply the denominators, 3 times 6. Now this does reduce. 2 goes into 2 1 time, and 2 goes into 18 9 times. So that would be our fully simplified answer. But what we could notice is actually this 2 could reduce with the 6 first. So we could write this as 2 times 3, and this 2 in the denominator of the second fraction could reduce with the 2 in the numerator of the first fraction. And then we'd have 1 times 1 makes 1, and 3 times 3 makes 9. So we're going to remember that you could write each of these as a factor and reduce before you multiply. That comes in super handy because if we had to take x squared minus 16 times this trinomial, it would be just a lot of those rainbows and really big numbers and lots of high powers. So let's see what we can do. First of all, I want you to notice we'll have another packet edit here. If we change this to x minus 9 on triad 3a, make it a little easier. So I've factored the numerator with the difference of squares, and then I factored the numerator and the denominator over here. Remember, we can reduce within the same fraction, but it's also legal now to reduce, kind of cross-reduce, if you will. So a numerator and a denominator anywhere can cancel, and we are left with x minus 4. That is your final answer. If they ask for the domain, okay, we want to make sure we consider all of the originals. So we would say it would be all real, except x could not be 9, or -10, or -4, coming from these values that were in the original. One thing that can kind of validate the idea that we need to look at the original x values that make the denominator 0, not just the reduced one, because here there isn't even a denominator. If you would actually graph this entire thing in Desmos, you would find holes or errors in the graph at the 9, the 10, or the -10 and the -4. So over here, now we have 3 terms. It gets a little crazy, but each of them is factored. And so if we were going to reduce, we'd have our x plus 3 here, and our x plus 3 here cancel. And we can actually reduce numbers like normal. See, we have a 3 and a 6. So if I had a 3, 6, that would be just 1/2. We can reduce our numbers like normal. We also, these 4s are on the same level, if you will. They're both in the denominator, so they don't reduce. We could look at the x's, though. Here I have an x, and x squared was x times x, so 1 is gone. So now I need to see what's left over. I've got an x left right there, and an x minus 6 in the middle. And then in the denominator, I've got the 4 and the 2. Multiply those, that'd be 8 times 4 is 32. And then I would have this x plus 3 left. So it didn't reduce quite as nicely as the first one. Again, back to our domain restrictions. Everything, x could just not be 0 from here. It could not be negative 3 from the middle fraction, and it could not be negative 3 from the second fraction or third fraction. So those would be our only domain restrictions. So now back to the regular example 3, since we did the try it 3 first. If I was going to do this one, remember a product is just when you would multiply these things. So I would have the 2 times 3 could make 6, or I could see it reducing here, but let's say I didn't, just for the heck of it. 2 times 3 would be 6. X to the 1 times x to the 2 would be x to the third. And then my y, all over 4 in the denominator, y, and z times z is z squared. So to reduce that, I know that 6 and 4 both have a 2 that goes into them, so I'd have 3 halves. My x to the third will stay because there's nothing in the denominator. The y's are going to cancel because I have one up top and one on bottom. We could have seen that here. And then I just have the z squared. For part B, I've factored them all. Remember, negative 3 wouldn't work, negative 1 wouldn't work there, and 2 wouldn't work. So if they're asking about the domain, that's what x cannot be. And then if we have our factoring here, we'd see that one of the x plus 1s will cancel. And then we have an x minus 2 that will cancel. So we are left with a 5x here and another x there. So I'd have 5x squared. And in the denominator, I'd have this x plus 1 and that 5. So even there, I'm seeing that I missed a 5 to reduce. So my final answer would be x squared over x plus 1. Example 4 is still asking for the product, so you'd be multiplying. But notice how the first one's the only one with the fraction, and I have factored that denominator there. But the second one doesn't look like a fraction. That means it's just over 1. So taking out an x and factoring that one, we could now reduce our x minus 2's. And from there, it looks like that's about all we can do, actually. So we would just have x plus 2 times x plus 6 all over. Oh, and there I did it again. I didn't look good enough there. Those would have canceled. All over x squared plus 4. So there is my final answer right there. Your domain, of course, they don't ask, but it would not let 2, negative 2, or negative 2 go into there. There would be some imaginary roots there as well. By this point, you're getting the gist. It's looking really easy, especially because all these are factored for you. So keep in mind, we'd encourage you to be able to factor. I am not going to show the products on these ones, but again, if they're factored, just start crossing things out and you'll be able to figure out your final answer and discuss your domain. You will want to check the packet answer key for answers on each of those. So we're going to divide rational polynomials, and that means we're going to divide fractions. So let's just talk about real division. 10 divided by 2 means how many times does 2 go into 10? So we knew that would be 5. 2, 4, 6, 8, 10. Repeat that phrase here. How many times does 1/3 go into a half? So if we cut something into a thirds, we would say how many times does this 1/3 go into half of it? Well, that'd be 1/1/3 and then half of the other third. So it's actually 1 1/2. But to get that, we teach that you would take 1/2 and instead of dividing by 1/3, which would look like this, and that's too much stacking, we would times or multiply by 3/1 in your numerator and denominator, and you would get 3/2, which is 1.5. These would cancel. We oftentimes call this multiplying by the reciprocal. So the good news about dividing rational polynomials is it's actually just multiplying by the reciprocal. You're going to flip the second fraction. So let's take a look here. We've got our first fraction. Notice the edit of x squared minus 1, and a quotient means divide. Everything's been factored, but instead of dividing by these two, we actually flip them now here. You'll see the 3x and the 5x have switched. That's because dividing is multiplying by the reciprocal. Then you just go on to business as normal. Everything's been factored, which flip the second fraction, and we now can cross out like terms. And remember, that includes things that are in opposite fractions. Here is our final answer. Note this packet edit. Again, instead of dividing, I've changed it to multiplying and flip them, and you can reduce. Here would be our final answer. Check your packet for the answer to B.